Okay, welcome everyone. Oh, just installing. How'd you go with your buffers questions? As I said, buffer is one of the hardest questions you can get, and I printed some like in a trial and HCC question that we had before. So I give you some clue about what type of question you will get in the buffers. Guys, we will be one of those type of questions. You can't get the questions out of that range, so make sure you practice that. We're going to do more practice on those questions anyways. So don't worry too much about those buffers for now. Next week, yes, we can finally do a practical test. So it'll be part A and part B. Part A would be first group doing the titration and doing the calculation within 40 minutes. Second group will do some question, including module 5 too. So I need to explain some of the module 5 this week. Okay. Yeah. Okay. Let me just share that. Okay. First of all, I give you some notes, missing notes from your workbook. It's about the salts that I talked about last week. I gave it down, okay. So this explains you that what's a salt type, what are the salts, what's the type of salt we discussed last week. So remember that we're keeping using those conjugate acid and conjugate base contents to explain, to understand about the acidic salt, basic salt is something that produced from the different type of titrations. Okay, one thing that I need to clarify before we start the buffer again. I give you some summary of the buffer, by the way. One, I think it was you, Danny, like asking me about the equivalence point. Okay, I give you the better definition than like just saying the hydrogen concentration same as the hydroxyl concentrations. The equivalence point is somewhere we're saying that it's we have the same amount of moles according to point where we get the same amount of moles according to the stoichiometry. Okay, I tell you what I made in here. So for example, when we sodium hydroxide to the hydrochloric acid, it's pretty obvious that when we have the same number of the mole for the sodium hydroxide hydrochloric acid, okay, that means that the amount of the mole of the sodium hydroxide is same as mole of the hydrochloric acid like that. But when we have a different type of titration, for example, ammonia to the hydrochloric acid, it won't be about the amount of the hydroxide ions and hydronium ions. It's more about amount of the ammonia is the same as amount of the hydrochloric acid that you have at the equivalence point. Okay, so this kind of gives you a better understanding then why the titration between the weak acid and weak base and strong acid would have the equivalence point that is less than 7 for the pH. Because stoichiometrically, they have a 1-to-1 ratio. So having that same number mole means that we have a more of those are released in the hydrogen ion than ammonia due to what? Strength of the acid. In the case of the sodium hydroxide to hydrochloric acid, as they have the same, if they both are strong, 100% release, 100% release. So at the point that they have a stoichiometrically same number of moles, 1-to-1, have a neutralizing everything. So that the pH at the equivalence point must be 7 in the reason. Okay, does it give you a better understanding about equivalence point then? Okay, so remember that end point is the permanent color change of your type of indicators you use. So we need to choose the suitable indicator in that reason. Okay, yes?
But then wouldn't it like react as you put it in?
Mm.
So it's like the concentration of, let's say, hydrochloric acid would go down as you put in.
Yes, if you put in the hydrochloric acid into that ammonia.
Then how do you get like equal stoichiometric ratios?
Oh, we believe that because we know like in this type of the acid and bases when it's strong, when it's weak. So we can approximate that equivalence point from that kind of observation we can consider in there. Because we kind of make an assumption in here, if these two have the same stoichiometrical moles, means that this must release more of the hydrogen ion. That's represented by the pH less than 7. So yeah, this is more about like an observation, kind of the statistical data we obtained, and therefore we're using that from the past experience to reflect onto the present experiments now. You're right, Ashley?
Is NH3
Weak base. This is why at the point they have the same number of moles, this is more releasing the hydrogen ion, therefore having the less than pH 7. Okay, so do not get confused about equivalence point and end point. It's a common question to actually get in the school exam a lot, in the practical tasks, in your trials. Maybe not in the HSC. I haven't seen the HSC question related to the equivalence point, but in school practical tasks, especially if you have the practical tasks in your school, and Carlingford and Epping Boys probably having that this term, then you might get similar questions as that too. Okay? All right, let's move on to the buffer. So I give you some more summary of what we learned last week about the buffer. Okay, let's just fix that. Good. So last week we started learning about buffers. As I introduced the buffers, buffer is one of the hardest, and probably the hardest topic to learn in year 12 chemistry. It's not easy to understand. So for the type of the buffers, okay, let's think about what the questions you get from the buffer. If you get a buffer there, okay, the type of question you get from the buffers is, sorry, the camera is a bit playing up today. Gotcha. Oh, not following. Oh. Okay, better. That's okay. All right. When we're talking about buffers, think about the definition of the buffers first of all. Definition of buffer is a solution that's made of what? Made of the weak acid plus the conjugate base, or the weak base plus the conjugate acid of that. So when we're preparing the buffer solutions, we're basically preparing with the mixing two solution of the weak acid and conjugate base, or weak base to conjugate acid. So what does it do? It is resisting, or we call it buffering, the change in the pH when we add it when small amount of the strong acid or the base are added. So I show you like a bit of calculation that how the buffer is resisting, therefore the pH change would be minimum. But now the reason why I'm saying the small amount is if you exceed that amount that you have, it's actually going over the limit. Means that it's not really working as a buffer anymore. It will be working same as just water because it's fully neutralized. Okay, example of that. The things you need to know about the buffer. The second part is that you need to know how to prepare the buffer solution. And as I introduced last week, there are two methods. One, you basically mix the two, a weak acid and the a conjugate base solutions together. So for example, thinking about weak acid, I'm mixing that 100 mils of the acetic acid. Okay, I have another plus that another 100 mils of the sodium acetate. That is what? The acetate is a conjugate base of the acetic acid. Then you're making that solution of the 200 mils of that acetate acid. and the sodium acetate inside there. Okay, so you had questions about how to find the pH of this buffer solutions. Then we kind of use the ice table and thinking about concentration of that, and therefore finding the resultant solutions too. Okay, this is the first method. The second method to making the buffer solution is you're adding. This is kind of general what we do. Adding the sodium hydroxide, a strong base. For example, sodium hydroxide into a weak acid solutions. But in that case, the amount of the N of the sodium hydroxide must be less than N of the weak acid. This is conditional. So what that means is this. Example, assume that we had 100 mils of the 1.0 molar sodium acetic acid. Here like that. What I do here is I'm only adding a few drops, say like 10 mils of the 1.0 molar and sodium hydroxide. Now, considering the amount of that we have, this having that in terms of number of moles, this has N is equals to CV, having given you the 0.1 mole of the acetic acid. In this case, N over CV, that would be 0.01 mole of the sodium hydroxide. So remember that I'm adding the sodium hydroxide into the acetic acid, and according to the reaction between these two, this will now producing some sodium acetate. Okay, when they're leaving some acetic acid too. So leaving some, some water, sodium H2O formed there too. So as your sodium hydroxide is the limiting reagent, what happens? It's all get consumed. It all get consumed. I mean, all kind of removed, all kind of reacted, producing that. So this means this will now producing the N of the sodium acetate, which is same about 0.01 mole in that solution too. So resulting that what? As a part of that, we get the 110 milliliter of the some acetic acid, okay, and the some sodium acetate. Amount of the sodium acetic acid would be 0.1 minus 0.01, giving you 0.09 will be remained. This would be 0.1 will be produced too. So this is the second method, and technically we using this a lot to make the buffer solution rather than using this, because sometimes it's hard to prepare the separate solution of the sodium acetate. This is easy to prepare and easy to perform in the school laboratory as well too. So when we're making the buffer solutions, I'm giving you some small amount of sodium hydroxide, but preferably we try to make that the same amount of the acetate and acetic acid. So instead of having the 0.01, we try to get the 0.05 and matching the balancing in those two. So it's working as the good ideal buffer solutions too. So this is the second type of the second method to prepare the buffer solution then. Remember that we can either prepare by mixing two or reaction between the weak acid to the strong base and making the strong base to be a limiting reagent. Okay, now 3, you also need to know the function of the buffer. You probably have that in your homework about asking you about how the buffers are functioning. For the buffer functioning, okay, bring that CH3 COOH. First of all, the reaction between acetic acid 2 and sodium acetate would be something like this. We get the acetate aqueous plus hydrogen ion in terms of the net ion equations. Okay. Now, have a consider about here in an addition of the acetic strong, let's say acid first. If I added the strong acid to this buffer solutions, think about the consequences. First, what does it do? The acid will first react with, not the acid, with the conjugate base. Okay, so in terms of the equilibrium, you might think about the Le Chatelier's principle, or like a kind of shift to the reaction to other side there too. But first of all, this is resulting that means that increase the concentration of the acetic acid as a result of that. Because what happened when the acids reacting, so for example, I'll show you that. Example, when the hydrochloric acid is invaded into the buffer solution there, it will be reacting with the acetate, yep, producing the acetic acid. So what does it do? This means that decrease the concentration of the acetate and also increase the concentration of the acetic acid as a result of those. Does it make sense? Now, you can use the Le Chatelier's, and it is quite recommended to use the Le Chatelier's principle, which is we learned in the module 5. Guys, think about it here. We decrease that, we increase this. Yep. Then what happens to this equilibrium system? As we have a greater amount of the product reactants, smaller amount of the products, what does it do? It will shift the reaction towards to the right-hand side. So what does it do? We kind of minimize the amount of the hydrogen ion produced. Does it make sense? It will increase the H, but not as much as the strong acid. This means that shift the reaction equilibrium to the right, but the hydrogen ion increase will increase, but not significantly. Why is it not significant? Why is it not really significant? Because we have to follow that due to the Ka, small Ka of the weak acid. And the Ka for this weak acid is known to be 1.8 times 10 to the power minus 5. Have a think about meaning of this smaller Ka. Means that it's not really favoring to move on to the product side. It will actually rather stay on the reactant side or here like that too. So yes, there will be a shift, but it will not increase the amount of the hydrogen ion not as much as we expected. Then what about the addition of the strong base? Give us more details about this. Then acid, weak acid, so it'll be the base will react with the strong base, the weak acid, which means sodium hydroxide came into that system, then it will be reacting with the acetic acid, producing that sodium acetate and leaving the water. So what does it do? It means that it will increase the concentration of the acetate, but it also decrease the concentration of the acetic acid. Does it make sense up to here? This means what? As a result of that, it will make a shift to the left, making the shift to the left, but not significantly. Due to, again, the Ka value over here. So even though we have an output of that, it will make it more of the weak acid, basically, or the conjugate base of that. So this is something somewhat very different to that when you're adding some strong base or strong acid to just into the water, and then I'm expecting that the pH change will be kind of minimal, or like a change would be like something just 1 to 6 weeks. Make sense? Okay. Now, can you see that you have 1, 2, 3, and you also need to know one more, the uses every day. Uses of the buffer. So where do we use the buffers to? We use some buffers in first in our like swimming pools. Remember that the pH of swimming pool is ideally we want to get the approximately 7.2. So after the heavy rain, like what happened is, because rain itself contains a bit of the acid in that, if the water, your swimming pool water is not buffered, means that you will accepting all that strong acid, therefore you're making the acidic. So you're basically swimming in the acidic pool. We don't want that to happen, so we put it into something like hypochlorite, or Cl minus is the buffer agent that we use. So this is working as a hypochlorite, and so it means we have a buffer of the HOCl and sodium OCl. Let's put it into the buffer solution, into the swimming pool as a buffer, so that it can resist the change in the pH. This is the first use and quite popularly used in exam questions. We have one question in the HSC in 2022. I'll show you that in a second too. Okay, there's 1, 2. We can use the buffer in the natural world, or like in nature. So, 2 examples. We're using the buffers in the blood system. Okay, for more information about blood system and buffers, it's actually provided in at the back of your workbook. Have a look at the last page. Can you have a look at the last page of buffer and your workbook, please? You should have that under the appendix, the very last page. Very last page. Yep, appendix there, buffers in the natural systems. 2, one is the blood system, one is the carbon dioxide that's using in the seawater. Now guys, memorize this. Okay, I mean, this is all I can say. You will actually get the questions asking you that how the buffers use the natural world. Now, for the blood system, we're using the hemoglobins, like using the CO2, and as a buffer, and the blood itself is kind of buffered. And this is the reason why after you're drinking some acidic soda drink, your blood doesn't go change the pH quite a lot. You can maintain the pH of your system, and pH in your body system is something super important because it will affect the enzyme activity straight away. Now, CO2, if you haven't learned that in year 9 and 10, bit of like in the carbon dioxide exchanges too, how the seawaters can exchange that. So think about the seawater itself too. They do not change, seawater doesn't really change the pH quite a lot. Even though it's got a heavy rainfall, it has lots of these CO2, some of the agents can change the pH. It's kind of resisting the change too. So important to remember, including the chemical equation. The chance you get this question, the natural buffer, in your trial is, I would say 50-50. It has a quite high percentage because when I collect the some data like every year, half of school get the questions about natural buffer, half of school don't. So I don't know whether you get it or not, but just prepare that. You may get that in the HS examination as well too, so there's nothing to lose about it. But this is something that you can prepare a day or night before your exam again too. So make a list of something that you need to memorize the night before, the day before, so that you don't need to spend too much time. But if you can memorize from now, you're quite prepared. So how many types? We have definition of the buffer. We have the the preparation of the buffer solutions. The functions, how they can operation of buffers. Example of buffer. Okay. Another thing is the calculation of buffers. Okay. So how many types? 1, 2, 3, 4, and 5. Those 5 types of the typical buffer questions we get in the trials, including the calculation buffer in the calculations. All right, the 5 is the type of buffer question. So I'm only expecting the 5 types. You won't get the question out of those type. I haven't seen any questions out of those type yet. I mean, if you're super unlucky that you might get us out of those 5 types, then you're not the only one getting unlucky then, okay? So in that case, try your best to get the best mark. But if you get those 5 type questions of buffers, try to get the full mark for those, because I'd explain you like what type of questions you would get. Okay, so calculation is, I picked one of the hardest questions maybe, but one of the, it's kind of doable questions. So let's have a look at the, did I give you the practice question yet? No. Did I give you this? No. So have a look at this buffer practice question. Here you go. Okay. I'll leave that for here now. There are 7 questions. I got the questions from the different, like a HSC trial paper in different schools. One from Cheltenham, one from Pennant Hills, one from I don't have the Cherrybrook though. One from Epping Boys, one from Carlingford. Okay, I try to get the buffer questions in every school in this classroom now, but you realize the questions are something that's predictable. So let's have a look at the question in there. Let's go quickly on the question first of all. 1. Students are attempt to produce the buffer solution as a part of the investigations. However, they cannot agree on which substance should be used to prepare the solution. So, for each student suggestion stated it is correct and justify your answer. What is this about? This is asking you whether making these are making the good buffers or not. Means that you need to understand about what the buffers, okay, or the definition of buffers, and stating that one or two students are the incorrect way to make the buffer. B. Using an example, describe why buffer systems are important in nature system. How many marks? 3. That. Simple as that. Okay? Use an example and the chemical equation as well too. You can either use the blood system or you can either use, okay, don't worry, you can find the answer for this question at the back, the last page of your workbook. It has an appendix there. Just memorize that. That's a sample answer for every single question type. Okay, let's quickly move on. We're going to do every single question, by the way. 2022 HSC question. Question 34. I even memorized the question number. Okay, swimming pool question. And this is a pure calculation. And we picked this is one of the hardest questions in that year because people get panicked like they didn't know how to do it. Okay, so I will ask you to do it later, but then now. 3. Calculate the pH of solution formed when 150 ml of the 0.05 molar sodium hydroxide is added to 35 ml of the 0.025 benzoic acid. Okay, what is this? You're adding some sodium hydroxide, the small amount of sodium hydroxide, which is a strong base, into the weak acid. The question didn't really say this is making the buffer. Where did I get this question from? This is a 2022 North Sydney Girls HSC question, the last question, question 35. 7 marks calculation question. Yeah. Oh, guys, it doesn't mean like, oh, I'm not going to get the question because North Sydney Girls. This is a trendy questions I would pick. Okay. After that, after HSC questions, schools and some trial question paper makers are following those trends in the previous HSC. If you didn't understand this is making a buffer, you have no chance. You probably get 1 or 2. But if you understood that, oh, this is actually making a buffer solution, and find the pH out of that, you just think, oh, this is exactly or something very similar to this type there too. The Ks given means that you might need to use an ice table. Not might, you must use the ice table too. Okay, we got to do this question as well. Question 4. As a part of the chemistry course, you have carried out investigation to prepare buffers and to demonstrate its properties. Describe how you carried out this investigation, include the conclusions reached and any risk assessment made. How many marks? 7. Ooh. What is this about? How to prepare the buffer solution, including the safety precaution. How do we test it? 7 marks. Where did I get Penn and Hills? This is your questions the year before. Okay, so this is what I'm saying, that you will get a method question. I don't know what module. Okay, buffer was one of that too. It was quite unlucky to get a buffer, by the way, because we didn't expect the buffers. We had that. But remember that still, this is one of the type of the question I talked about today. 5, Cheltenham, your schools, and Epping Boys, you guys share the same question in the same year. Okay, let's have a look. Student used a data logger and a pH probe to measure the pH of the solution of the acetic acid and equimolar mixture of the acetic acid with the sodium acetate. Next, they added hydrochloric acid to each solution, recording the pH as the HCl was added. The results are shown in the graph below. So you'll see when you're adding the hydrochloric acid, this is not buffered. You only have the acetic acid inside. So you see that pH is going to drop sharply down. Now, what happened in here? As this is buffered, you see some resistance or like buffering to change the pH. Then what is the question asking you? Question is asking you, explain the different shapes of the 2 graphs using a relevant chemical equations to illustrate your answer. 3 marks. Now, did you figure out this is about the buffer question? And this is a trick. The examiners don't really use the word buffer in the question. So it is your skill now, it is your understanding, based on your understanding that, oh, you need to realize that this is a trick. This is actually a buffer question. Okay, so very important to understand, and think about the marking for the buffer questions. The least is 3 to 4, the highest will be 7. There's a good chance you get a higher marks in that this year on the HSC and trials too. B, pure hydrogen chloride is a gas. What volume would have been dissolved in the 2 liters of the water to produce a solution with the pH 1.25? Module 2, the ideal gas law question in trials. Epping boys and Cheltenham, by the way, again. Yep. 6, this is the Catholic paper. I forgot the year, 2022 probably, okay. The graph shows how pH varies for the solution as acid is added to it. Explain the shape of the graph. So what you see there is, we're adding some acid, but you're seeing that there is not much change in the pH. But after a certain point, it kind of drops. What is this? Again, buffer solutions. So you got to explain that why it is resisting. What happened in this region? What happened at that point? That's basically when you consume all that conjugate base. It's running out of conjugate base. There's nothing to resist the pH change. That means it will be it's working as the water, dropping the pH straight down. Okay, 3 marks. But no clue, no explanation, no word about buffer. B, the chemical process is important in the various chemical system. Using appropriate equations, outline the chemistry involved in a named natural system. What is this? That. Again, 2 different sets of the trial papers, exact same question, exact same marks, just changing the style of the question. That's it. Okay, prepare that. It's got to be like 3 to 4 marks for those. It's so easy to get it, like to get the 3 out of 3. Okay, 7. To avoid the eye and skin irritation for the batters, swimming pools are maintained with the pH of the range of 7.2 to 7.8. To help achieve this pH, we're using the sodium hydrogen carbonate. Maybe we can use that. Okay, what is the physical property of the sodium hydrogen carbonate that makes it suitable for use in swimming pool water? Any guess? Why do we use sodium hydrogen carbonate? Any guess? It can be working the weak base. Physical properties. It'll be soluble, yeah. It'll be soluble, yeah. You gotta think about the word in here. Physical is not a chemical property. The weak base is actually a chemical property. So trick, isn't that tricky? Isn't that like a naughty question? That you might not notice that the physical properties. How many people got it wrong? I remember that about 80% got it wrong because of that. They didn't realize it's the physical properties. Okay, guys, that's a trial questions coming in 150 days. Fresh. Define the role of the buffer in the aqueous environment. Easy in it by now, okay? C, explain how sodium hydrogen carbonate would act as a suitable buffer in a swimming pool. Provide equation to support your answer. That's a question. Again, there are some calculations, there are some explanation, but guys, the reason why I'm giving you some collection of those buffer questions in the different trial paper is I just want to give you a clue that this is easy to prepare. They are predictable, okay? And yes, they're hard, but I really want to say that this is a doable question. Should be a doable question. And you should aim to get, for this is a 3, 1, 1, that's how many marks? That's 2, 5 marks. You should aim to get at least 4 out of 5. And so yeah, you can get it wrong for the question A. You don't notice that physical property, but you can use that. Does it make sense to all? By the way, where do we get this physical property from? That's from Module 1. We learned that in the Module 1. And this is how the examiners mix use that Year 11 contents to Year 12. But it doesn't mean you need to study Module 1 again. Okay, don't worry, you will get the 20 trial set papers to practice later. Maybe 30. How many did I give you last year? 35? Yeah. You might see like Dongyo have the thick chunk of pile of these trial papers for chemistry, for the physics. Yeah. All right. So these are the trial questions like you can practice, and we're going to do some of those questions today. Let's start with question 1. For each of the questions, it says 6 marks. So I give you about 6 minutes to answer this question first of all, and we're going to go through the answers together. And at the end of the class, I give you the sample answers for all those questions. So try your best. It's always you need to challenge it, to push it, and then see the answers and then challenge it again too. Okay. So let's try that. 6 marks. How are you going to answer these questions? Homework marked. Okay, I'm gonna give you for Ashley. Oh, here you go. Ash, this is your school trial paper in 2021. Skip all the module 6 and 7 and 8. Find the module 5 question in multiple choice, okay? And once you finish that, let me know, then I will send you the answers for that. Okay, thank you. Oh, thank you. Yeah. Hello. First day back. 욕심이야. 아 맞다, 잠깐만 이거 까먹기 전에. Okay, I should try this one too. Well, 5 is 6, but okay, finished. Okay, right. This is the sample answer for those questions. Aaron, could you pass one back? Thank you.
Yeah.
Ashley. Oh, sorry. No, last one. Now, I will guide you how to use those sample answers. Those sample answers in your, because I will give you lots of the sample answers, the marking criteria, and you need to learn how to use that correctly. So let me just send it to you, Joanne. Give me a sec. First, guys, do not read the sample answer first of all. Read the marking criteria in the table. Okay? Because when the markers are looking at your answers, we're not looking at your answers straight away. We're looking at the marking criteria given here. Think about how you're going to give the marks for each your answer. And then we pick up the pen, the red pen, and seeing that whether you tick those dot points of the marking criteria or not. So for this question, to get the 3 out of 3, you need to correctly identify the correct students and then provide a justification statement about the suggestion of the all three students. So if you did it right, you get 3 out of 3. If you first, by looking at student 1, I can tell, oh, H2SO4 straight away. Oh, that's a strong acid. We can't make the buffer with strong acids. Incorrect. We have a H2CO3 and conjugate base of that. Okay, weak acid, conjugate base. We can make it. H3PO4 and CH3CO minus. Okay, that's a weak, but I don't see the relevance between these two. So this is not a what? The pair of the conjugate acid and base. Incorrect. Student 2 is only the correct answer. You need to justify that again, saying, oh, because the student 1 is incorrect because the H2SO4 is a strong acid, and we can't make the buffer with strong acid. This is the right answer because we made it with the weak acid and conjugate base pair. This is incorrect because that's not the conjugate acid and base pair. Okay, now try to think about how you're going to answer the questions after you read that marking criteria. And then compare the answer to your, it's a sample answer to your answer. The sample answer provided are sometimes, or most of the time, not perfect. So there are some students coming to me, oh, hey, for the retest, by the way, I wrote the exact same for the for my retest in the sample answer. I'm like, why didn't I get like a 3 out of 3? I'm like, as I said, the sample answer is not perfect. You need to think about how you're going to make the perfect answers from the sample answer as a reference. Does it make sense? Okay, don't trust that sample answer too much. Sometimes you need to write more than provided there, especially for the 7 markers and 9 markers later on. The natural buffer system, as I said, you can use either your blood system, which is using the hemoglobin, or you can either use that something in your the fresh water on the oceans. This sample has provided that, but have a read the marking criteria again. It's giving you, describe the importance of the buffers in the natural system, refers to a specific example, include the relevant equation. So you must include the equation even though the question didn't specify the equation in the question there. Okay? Make sure that you put the relevant chemical equations every single time for the chemistry question, even though the question didn't state that, because that is stated in your marking criteria. That's same for the module 7 too, even though this question didn't state that, you need to write it down, the relevant chemical equation there. So if you chose the fresh water, you need to show the, this is referring to that, H2CO3, with the water, making that into the H2O, hydronium ion, and with the HCO3 like this. I'm using that, the student 2's example. So it'll be a good relevance showing the A and B, but it doesn't have to. I mean, yeah, it doesn't have to. You don't have to use student 2's buffer. You can use acetic acid, but make sure you talk about the buffer system in buffer in the natural system. Okay, you will get 1 in your half-yearly test in 2 weeks. Half-yearly, module 5 and 6 combined, by the way. Okay, so may see you on Thursday for that. 2, now, without looking at your answer, I would like you to try this question. Oh, by the way, if you can give the markings for the question 1, give a marking, try to mark it really harsh. That what would you give to your answer out of 3? Was it 3 out of 3? Was it 3 and 3? What would you give to your answer to in the markings? Okay, that's what my markers got trained basically. They're all trained with that method. You need to learn how to mark your work independently. Yes, markers providing the markings too, but you need to know. So as soon as you read the question in your head, you got to think about what are the marking criteria. That is the exam strategy. Okay, you're not just narrating down all the answers you memorized. That's not how you get a 3 out of 3. So mark it really harsh. That if you think like that answer is not really suitable or you can get the point of the marking criteria, you don't get a mark. Okay, try to mark as harsh as you can because, as I said, chemistry teachers are the harshest markers in your school. Especially Cheltenham, your schools are, I know they're really harsh. Really harsh, even harsher than what I imagined. Okay, you don't have to share the marks to me. You don't have to. I'm not going to ask you like what marks you get, but have a think about how you're going to develop your answer, how you're going to develop your answer for those specific questions too. Okay, that's how you need to improve. And same for you actually preparing for your coming test on Friday too. Okay. Now, try the question 2, HSC question, 4 marker, question 35 in HSC 2022. Give it a go. And I will actually explain the answer because the answer is not really in details. Give you 5 more minutes. Okay. Need a little more time? No? Okay. Guys, what are you feeling? What are you feeling now is the what the students in 2022 felt as well. They felt like, oh wow, what is going on in this question? As I said, it's one of the hardest questions in that year, especially in the exam conditions. I remember the students, like the top students, actually spend, even though it's a 4-marker questions, they spend about 10 to 15 minutes to solve that. I'm not too sure whether they got the full answer, like a full mark or not. Okay, but if you think about it, this is all the things that are all relevant to what we learned throughout Module 5 and 6, especially Module 6 in this case. So sodium hypochlorite is an active ingredient in the pool chlorine. It completely dissolves in the water to produce the hypochlorite ions, which is OCl-, which undergoes hydrolysis according to following equilibrium. So hydrolysis simply means reaction with the water. Okay, so it produces the hypochlorite. So that's the acid, hypochloric acid, hypochlorite acid, and hydroxide there. So the equilibrium constant for the reaction given at 3.33 times 10 to the power minus 7. The pool chlorine to be affected, the pH is maintained by different buffers at 7.5, and hypochlorous acid concentration should be 1.3 times 10 to the power minus 4. Calculate the volume of the 2 molar sodium hypochlorine solution that needs to add it to a 1 times 10 to the power 4 liter pool to meet the required conditions then. Yes, what a question. This is something that's not easy. So let's start one by one in here, first of all. Try to understand what is going on in the question. So you have a pool, swimming pool, that is 1.00 times 10 to the power 4 liters of the swimming pool. So we're going to go backwards for this question to understand what is going on in there. Okay? So you have this pool, this size of pool. What you want to make there is, you want to make that the pH of this pool to be 7.5. Okay? And the concentration of the HOCl in that pool must be 1.3 times that 10 to the power of the minus 4 mole per liter. So this is the aim. We want to make the swimming pool of this size. We have a pH of this and a concentration of this. Everyone okay to understand the question there? Then what you have to provide it is you're given that sodium hypochlorite, OCl, given. So you imagine that, you can imagine like, oh, you prepare, like you get in the packets or there's a whole like a bags of this sodium hypochlorite. The concentration is given as 2.0 times mole per liter. This is super concentrated. Then simply, we need to add some sodium hypochlorite into that, NaOCl there, to make that input to be the pH of 7.5 and concentration of that. Now, do you now understand what is going on in the question? So this is the techniques that we can use in the exam. So what we do is we're going backwards, because most likely in the first point, the first 2 paragraphs is explaining what's going on, what kind of chemical reactions we need to use. We don't need that to understand the question, first of all. We need to understand the whole picture of that, the purpose of putting the sodium hypochlorite into the swimming pool of this. Okay, remember that this is what we want to make. Everyone okay? Then, think about it in here. The total sodium hypochlorite, we're going to put it into that, we need to put it in, is, first, it'll be something that we use from the HOCl from the swimming pool, plus that OCl minus in the pool as well too. Think about what happened as we put the sodium. So, and we're going to rewrite that over here. So instead of OCl, when we put the sodium OCl into the pool, if that's salt or H, what it should be, sodium OCl, sodium hypochlorite, into the water, this will have the reaction of producing that HOCl plus that sodium hydroxide we produced. I'm just using what we have given the hydrolysis. But to understand the question better, just imagine that we're putting the sodium hypochlorite into the swimming pool. And that would be the reaction between sodium hypochlorite into the swimming pool water. Does it make sense to all? Okay. Then, in this reactions, can we think that the total amount of the NaOCl, the total that we get is first one from this HOCl. Okay, after we dissolve that into water, HOCl in the swimming pool in this reactant site, and the remainder of the NaOCl remained as a equilibrium. You okay, Donna? Yep. Danny, can I get it? Okay. So I'm basically saying this will be the total amount of OCl that we need to put it into the swimming pool. Everyone okay? Okay. Now, the desired pH we want to make the swimming pool is a 7.5. From that, we can get the pOH, because we have the OH, that's the same equivalent to OH minus concentrations, from the pH 14 minus pH. That is 14 minus 7.5 gives us 6.5 there. Then concentration of the hydroxide ion must be at the equilibrium after we all completely dissolve the sodium hypochlorite is the 3.10 to the power minus 6.5 mole per liter. Okay, so this is what we want to make. We want to get the concentration of the hydroxide ion to be this. Does it make sense? Okay. What about the concentrate of HOCl we want to make, which is this? We want to make that. So we want to make these two. This is what we want to make by dissolving that. Now, bring that KEQ for the given condition there. We have given HOCl times OH minus product divided by the reactant OCl minus here like this, from the given reaction there. This is the same as what? That's given as 3.33 times 10 to the power of the minus 7. That's given. Okay, at the equilibrium. Now, what you're given here is, you're given that concentration of the hydroxide, you're given the concentration of the HOCl in here too. Does it make sense? Then, you are able to find that concentrate OCl minus from the reaction is HOCl times OH minus divided by KEQ value by rearranging the formula. That is what? We have 3.33 times 10 to the power minus 7. On the top, we have the 1.3 times 10 to the power minus 4. That times that 10 to the power minus 6.5 here like that. Then you to get the concentration of the OCl minus, that would be from the answer 1.23 times 10 to the power minus 4 mole per liter. Okay, let me just write it again. 1.23 times 10 to the power minus 4 mole per liter. Let's write it again. That's the concentration of the OCl minus at the equilibrium. Okay, everyone okay up to this stage? I just found that at the equilibrium, this will be concentration of the sodium hypochlorite, which is, and then we got the concentration of that. Then chlorine species from that 10 to the power minus 4. Then whole thing, the NaOCl must be, we are adding up the concentration of this to the 1.3 times 10 to the minus 4. As we discussed that, the total amount of sodium hypochlorite we need to put it into the water. Okay, initially we put it into the water is amount that we dissolve in the pool, amount that is left over. This is the leftover. So you can think that as this is a leftover on excess or like excess sodium hypochlorite, and this is the amount OCl minus that dissolved in the water. Okay, so to get the total amount, what do we need to do? We're adding these two. So the total concentration of the NaOCl is then therefore, we get the 1.23 times 10 to the power minus 4 plus that 1.3 times 10 to the power minus 4 here like that. This will give you the total concentration of sodium hypochlorite, which is 2.53 times 10 to the power minus 4 mole per liter here like that. That's a total, or it was something appreciably total, or the prepared. To put it in, we're always going back to the question here, we want to put these into the swimming pool. This is the amount we need to prepare, amount of concentration. Okay, then initially you're given this much here. Then, after we put that into the water of the 1 times 10 to the power 4, that is the change in concentration. So what you have done, you diluted it. You diluted the amount. So you bring that, the dilution factor, C1 V1 equals C2 V2, the equation there. That concentration 1 is that 2. 2 times initial, we don't know how much volume we need to put it into that, how much will do. So I'm going to leave that as V1 first of all. But we know the amount of the sodium hypochlorite is 2.53 times 10 to the power minus 4 after we put it into the water, the swimming pool. What is the volume of the water? The swimming pool is 1.00 times 10 to the power 4 liter there. Then we can find the final volume using what? We can either use C2 V2 over C1 if you like to use that, the dilution factors. 2.53 times 10 to the power minus 4 times 10 to the power 4 divided by C1, which is 2. Then you'd get 1.3 liters in 2 sig figs, but have a check the how many sig fig values you're given. You're actually given 2 sig figs, so let's fill the 2 sig figs. So in the 2 sig figs, this is 1.3 liters will be added. Try to understand the question here. You need to put 1.3 liters of sodium hypochlorite into this swimming pool so that you are able to get the pH of 7.5 and the concentration of the hypochlorous acid to be 1.3 times 10 to the power minus 4. Okay? Not an easy question, as I said, especially like when people didn't think about, oh, what do I do with these values? So more than half of students, I remember that they wrote the value down, and then they were like, they didn't know what to do. So they show some of the formulas, some of the calculation, try to get some partial mark. Yeah, I think that's a good strategy. You may get like 1 or 2, but the top students, those students actually comes in the state levels, okay, or like in the top band 6s. They knew, like they understood that what is going on in the question by drawing like this kind of flow chart or diagram there. So they were actually thought about, oh, this is actually like we are finding that dilution. We're diluting that into the swimming pool. But once you think like it's actually a dilution question rather than the complicated Ka or complicated ice tables, this is a doable question, to be honest. After you heard the explanation, by the way. But this year, you will get to some sort of like questions like this, that you're giving some complicated situation, complicated like kind of scenario. It is your task to figure out what is going on in that scenario, and this is getting harder every year. This is why HSC chemistry is getting harder. Okay, it's getting more methier, getting more like scenario based. So practice those questions a lot. Okay. Let's do one more question, question 3, and then we're going to have a break after this. For the 7-marker question, I give you 10 minutes. Try it in 10 minutes. Okay, time's up. How'd you go? So as we discussed before, this is how we prepare to make the buffer solution. Okay, so to make the buffer solution, we prepare the batch quite a lot of the weak acid, put a little amount of the small amount of the strong base. So what we try to do that is we are leaving some conjugate bases as a result of that. So let's think about the reaction between sodium hydroxide, falling to the question there, and benzoic acid, that is C6H5COH, the aqueous. When these two are reacting to each other, the COH, the hydrogen for the COO groups, will actually release in the hydrogen ion, so it becomes to the salt. So it becomes to sodium benzoate, C6H5COO, the aqueous, and leaving that H2O liquid. Okay. Guys, this is just the one reaction between the first reaction, the equation 1, the reaction between sodium hydroxide to the weak acid. There's no reverse because that basically they're all reacting to each other 100%, producing this. And this is the point. So started from what we're given for sodium hydroxide by CV. That is 0.050 times 15 mils, 0.015. This will give you 0.00075 mole. Okay, that's the amount you're given. Then, amount of the benzoic acid you're given is C6H5COOH. That's the amount you're given. But again, the CV, which is 0.025 times the 35 mils, 0.035, then you should get 0.000875 mole. Now, this is a given amount. As you can see from the reaction ratio, that's 1 to 1 to 1 to 1. And the sodium hydroxide and that, I can say this is your limiting reagent then. So you can write it down as sodium hydroxide is the limiting reagent.